bismuth selenide, published in this paper, Jin Zhang and my students, and published in March of this year. So there we observe topology-driven quantum magnetic phase transition. When you change the level of the doping, you see the topology, electronic structure, the topology will be changing. So they drive some of the quantum phase transition. So I will not talk about that. So this is the paper. And since we have to, the starting material has to have some of the right band gap. So we did the band engineering by mixing of the bismuth telluride and antimony telluride. So the reason is can be explained by this figure. So that for the bismuth telluride, the Dirac count is very, very in the valence band. So it's very difficult to access the Dirac point property. Also the materials, as prepared materials of this one, is an n-type of conductor. On the other hand, antimony telluride, the good thing is the Dirac point is exposed in the gap. Unfortunately, this materials, as prepared material, is always p-type doping. So if you mix these two together, so you may, so by the concentration of the N carrier and the P carrier, and then you may get the something band structure something like this. So the Dirac point located the gap, and the Fermi energy may be very close to the Dirac point reach the charge neutral point because of the concentration of the N and the P. Okay, so this is the simple idea. Then the student did that, and you can see at the zero, actually zero without antimony, you see the standard band structure of bismuth telluride with the increasing of the amount of the antimony, the Dirac point move out, the Fermi energy go down. Probably not very clear here. This is almost the ideal case. You have the Fermi energy reach to the Dirac point near the charge neutral point. In all the cases, you have this linearly dispersed band. So this is very good. So after we get this right, we obtain this right band structure, this ideal band structure, then we on top of that materials, we did this chromium or ion doping. So here, very importantly, is you have to make sure that chromium only take the lattice side of the bismuth or the antimony. So cannot occupy the telluride side. Otherwise, you have the wrong doping. Also, the second very difficult thing is the chromium. The temperature for compound growth of this one is very lower than the 200 degrees C. But the chromium, usually, if you want you want the chromium mobile, you need a higher temperature because this is a metal, magnetic metal. So usually, if you use the high temperature, then this guy gets together machine cluster. Also, the decomposition of the material may take place. So you have to really control the growth quantity carefully. So for that, we use the low temperature growth, and this is the morphology after the chromium doping. And this low temperature morphology is quite okay. If you look at the atomic structure, you see most of the chromium occupy the lattice position of the bismuth or selenium, as you can see here. Also, the second good thing is that there is no clustering of chromium, as you can see in this high resolution temperature. So, chromium only occupied this position. There is no clustering. That is different from the manganese doped gallium arsenide. There are still some argue on the manganese clustering. So at all the doping level, we see the ferromagnetic odor. So that's very nice. Not the paramagnetic. And also the band structure, topology, no change, linear, even without at a different doping level. So then we have the growth, check the electronic structure, atomic structure, band structure, did the transport, made the map. So we do this kind of cycle. And so this is some typical picture of our machine use. Professor Ma's group and my group have this combination system. This is Professor Wang's group, and this is electromagnetic transporter setup. This is Professor Luis' 20 millicurie setup. students make this whole bar and so on. Yeah, I think I just, our goal, of course, is to achieve this whole system. This is the final, I just show you results. This theory is our experiment. So the agreement basically excellent at this temperature. Of course, since now the system becomes fully insulated, you don't need to consider this kind of mechanics. So this finalize the mechanical study of anomalous Hall effect. And for the last, I just mentioned one thing we are working by making this superconductor topological interface heterostructure. We are looking for this Majorana fermion. So some of the experiments already done in the Professor Jia's group in the Shanghai University in collaboration with us. So please notice the material is very important. Here we use the bismuth selenide, non-bismuth selenide. So the chemical property probably very similar. By that we can prepare very atomic sharp interface. So we see the proximity induce the superconducting gap in the side of the bismuth selenide. You can read the paper. But basically, in the world, a lot of people working on this topological insulator, even quantum anomalous whole system with the superconductor, even the ion selenide. Right? My group is working on this bismuth selenide and other topological insulator on top of ion selenide. I think we already get some results. So this is one of the most important directions in this field. Finally, I acknowledge the NSF, Ministry of Science and Technology, Ministry of Education, for the support, final support. Thank you very much.
Thank you very much for this interesting talk. Any questions?
Professor, I'm sorry, I have occupy your time.
No, not yet. Just a lot of time.
Hello. Dear Professor Xue, thanks very much for your interesting talk. I just have a question that based on the correspondence between Qikun Xue effect, Qikun anomalous Hall effect, I just want to know, is there any kind of such as fractional Qikun anomalous Hall effect?
Yeah. So by doing yes, that's the one thing we are looking for. Although it's very difficult to make by combine the different design the superlattice using this different topologies. We can see the fractional Hall effect. Yeah, the fractional quantized anomalous Hall effect. Yeah, that's more difficult. You have different data structure, not like very simple like this one. You can do that. There are some theoretical proposals experimentally. Experimentally is more difficult to do, but it's a good direction to move.
Thank you very much.
More questions? Okay. If no questions, thanks our speaker again. So we have a coffee break outside for about 15 minutes. Thank you.